at the University of Lyon 2. He is member of the LIRIS Lab, Laboratoire d'Informatique, Images et Systèmes d'Information. His main research activities are devoted to models and tools for image processing, image analysis, computer vision, shape recognition. More than 20 PhD theses have been defended under his supervision. He published about more than 100 research papers. And as I said at the beginning of the symposium, Serge collaborates for our greatest pleasure to the research project on augmented artwork analysis, computer-aided interpretation device for art images. Please.
Thank you very much. I would like to first thank the organizers of this symposium, and in particular Maria Giulia, Ralph, Pierre Luigi. It's a great pleasure for me. It's a bit also, it's a step in a real new world. I'm probably the only one of you that have no connection with arts. So it's my first step in this very interesting domain. So I hope my talk, which is very unusual for me, will be at a good level. I didn't really need, Maria Giulia just told me don't put any equations, don't put any models. So I hope it will be of some interest for you, even if it's well, I show you pictures, so that's easy to understand. So I first would like to begin with a the very initial message sent 1.5 years ago by Pierre Luigi on May 5th, 2018. It's in French. I try to read a traduction. So with other colleagues of Liège, Luxembourg, I'm trying to launch a consortium. The goal of the project is to create a prototype of assisted interpretation of artistic images, which leads to an application called the augmented artwork. It's an interactive device that, in front of an image, shows an open number of other images, thus producing a virtual museum. This application will be able to remember previous visits to museums. This will create an application that reflects the story of the personalized look. The goal is to be able to interpret the initial image by bringing it closer to other images. We can emerge reading paths in the image itself, which allow to observe it better, to explain it, and to appreciate it. So this was a very challenging project, and I said yes, I'm in. So we decided together to try to launch this consortium. It's not exactly the one that was initially proposed, but so the project has been sent to the ANR and is under evaluation. So my talk will be organized following this outline. I'll just give some words about my laboratory, the LIRIS laboratory, and the research team I'm a member of, the Imagine team. I'll give some word about what computer vision is for me. And this talk will illustrate a major change that has appeared a few years ago, let's say 5 to 7 years ago, and that has really revolutionized our research domain. I, of course, speak about deep learning. So then I will illustrate through mainly two research projects the way we were doing shape analysis before deep learning, and the way we tackle now this problem, now that it's evident that we cannot ignore this kind of techniques. And then I showed some very first contribution that could be contribution to the augmented artwork project, if, of course, it is accepted by the ANM. So some word about my laboratory. It's a joint computer science research unit, an unité mixte de recherche in French, which has a national partner, the CNRS, and 4 local partners, 2 universities, Université Lyon 1 and Université Lyon 2, and 2 engineer schools, INSA de Lyon and École Centrale de Lyon. We are about 150 permanent staff, either academics or full researchers, about 120 PhD students on 4 sites in Lyon. I am personally member of the Université Lumière Lyon 2 in Bron, like Pierre Luigi, even if his office is in ENS de Lyon, another campus. So this gives me the opportunity as a computer scientist belonging to a human social science university to be in contact with people of other disciplines, and I have several collaborations with other researchers of other main discipline, but it's the first time I'm trying to collaborate with people of arts or visual semiotics, and so it's very exciting for me, this new research topic. So my laboratory is organized in 14 research teams, grouped into 6 research poles, and I am member of the computer vision and pattern recognition pole, which is only composed of 1 research team, which is the Imagine team. My personal research activities in this team are on shape analysis, pattern recognition, machine learning. I've worked a lot on video surveillance, background modeling, motion modeling, trajectories analysis, multiple objects tracking in video sequences, multi-camera tracking, and so on. So you see that's very different from what we are speaking about. I have had several applications in medical imaging, in traffic surveillance, in logistic installation surveillance, in intrusion detection, in embedded systems and mobile development. I'll try to show you some of our realization in embedded computer vision. I've worked on augmented reality that can be of some help for the project. And I have several academic, industrial and international collaboration that are listed there. In this talk, I will focus, of course, on shape analysis for me, for a computer scientist, on machine learning, on collaboration we had with biologists. I speak about mobile development and on augmented reality through a certain number of projects we have led with this specialty. So a few words about computer vision. I don't want to give you a lesson, but just to maybe make it more concrete for you, and especially this evolution, this dramatic evolution that happened a few years ago from an era of craftsmen, artisans, to the era of kind of industrialization of computer vision through deep learning. So when we speak about digital imaging, we traditionally speak about 2 main domains. First domain is the domain of images. For us, it's unstructured set of very large set of pixels. And the other domain is the domain of models, of structures, of higher level domains, of lists of properties that somehow describe the contents of the images. What we call computer vision is the left to right arrow that tries to give an interpretation to this very large number of pixels. There is also a reverse arrow that also belongs to the main domain of digital imaging, which concerns a community that is quite separated from computer vision, which is the computer graphics domain. The idea is to start from a geometrical representation of a scene and to generate images from this description. I said these communities were separated. It's not so. They tend to speak to each other because it's very important to, when we try to better understand images and to construct correct models, to see if it could be these images could be generated from these models. So these communities have much to learn from each other. There are also looping arrows. What we call image processing is the transformation that transforms an image into another image. And of course, there are also transformations that transform models, basic models, into more structures, more semantic models, for instance. Just to give you an idea, this will probably be the only artwork I will show in my talk. Of course, for the computer, it's only composed of numbers, of small squares called pixels, which have numerical values. And of course, to understand that this is an old man with a gold chain, or that it's the old man with a gold chain of Rembrandt, there is a lot of work. This is what we call the semantic gap between these very large number of unstructured data and a much more compact data of much higher semantical level. I'll skip maybe this one just to say that in computer vision we decompose a low-level image processing, intermediate level, and higher level. And the intermediate level is probably what is the most difficult to cross this semantic gap between images and signals to models and structure. Just to give you an example of what we can do, some image processing operators that were up to a few years really manually crafted by specialists. I'll speak you about a very low-level operator, which is a Sobel operator. And I'll speak also of an operation that is important in image processing, which is the convolution. And you have heard this word when we speak about convolutional neural network. These new neural networks make intensive use of this operation, the convolution kernel. It's a matrix of a very small matrix. It's called a kernel or a convolution matrix of small size. Here it's 3 by 3. And the idea is that we will scan the image with this matrix by doing a very simple operation. The idea is to multiply the value of the pixel by this coefficient and to give the final value of the output pixel. You see that in area where the image has a constant value, this sum will be approximately 0. It will give a black output pixel. If we are close to a horizontal transition, then there will be a much higher value for light pixel and a smaller value for dark pixel, and the final output will have a high value. This, for instance, gives the result of the convolution of the initial image with the former convolution matrix. Of course, if you rotate the convolution matrix, you get other responses. This is the response to the 90-degree convolution kernel, and you can also imagine 45-degree or 135-degree mask that give different answers, different outputs to this image. You see that only the high contrasted area appear. This makes the information much more compact, much more easy also to understand for a computer. Of course, it's not enough to describe the object, but it's an important starting point. I'll show another short example. This is a photography, again, taken in ideal illumination condition, which can be considered as the model the computer has in memory. In our scenario where a visitor comes with his smartphone or a tablet, or is in the museum in front of this picture, the first task will be to recognize this picture. How can that be done? The picture is not exactly taken in the same illumination condition. Of course, the camera of the smartphone captures a larger area than the picture itself. So there is a frame, there are shadows, the colors are not exactly the same. So if you just compare the value of the pixels as numerical value, they would greatly differ. So we need operators that are somehow invariant in illumination conditions, invariant in translation, invariant in rotation, so that the picture can be recognized. So there are a lot of operators that can be used for that, but one of the most commonly used now is based on the extraction of sift point. It's not the only one. So if these interest points are extracted both on the model and on the captured image, this small number of points can then be associated to a local descriptor describing how the lighting changes around this point, how also the gradient varies, and how the different gradients are oriented around this point, how the scale of the point changes also. Sift means scale invariant features transform. So this is a very important thing that if you have two images taken at different scales, at different resolution, the descriptors of the interest point must be kept constant. So the lines that were drawn here describe for each point of the left image the best corresponding point of the right image. And you see that most of the time the match is correct. Sometimes, however, some points better match other points that are not in correspondence, that shouldn't be in correspondence. This can be then filtered by algorithms. For instance, this is a Randstad filtering algorithm. Randstad means randomized sample consensus. It's an iterative process that allows to remove outliers and keep coherent correspondence. So to sum up this part, what are the objectives and the main methods of computer vision? We need automated methods for symbolic visual data representation. These data have to be compact, but of higher level of semantics. That allow to efficiently measure similarity between images or between patterns or between textures for shape description and shape recognition. And this leads to the notion of shape signature. It has been the main paradigm for more than 50 years. The transition date is about 2012. I explain why. These features are based on Fourier analysis, on color distribution, on texture analysis, on discrete geometry, and discrete moments, on topological description, the fact that an object can be inside or outside an object, can have holes, something like that, on the graph-based representations, on visual words, or a bag of words that have spatial relationships between them. That's very important to pay attention for the spatial relationships the different visual worlds have together. And these were all what we call or what is now called as handcrafted descriptors. Progressively, all this science is being replaced by deep learning technique for less than 10 years now. And in particular, what are called the deep convolutional neural networks. So I just want to make some historical points. I skip very fast on that. You probably already have heard about that. This is the biological neuron with all these connections. And the first formalization, the first formal neuron can be dated of 1943. It's due to McCulloch and Pitts. There are a certain number of important dates, particularly in 1958, Rosenblatt has proposed the first architecture to learn a model with a teacher. This perceptron allowed to do in an incremental manner linear separation between shapes that were associated to shape descriptors. On the image you can here, it's a simple linear separation between cats and dogs based on two particular axes. And it really mimics the biological way of functioning of the biological neuron. Then, in 1969, Minsky and Papert put into light the fact that this perceptron was in fact very limited, and that some very basic function, namely the XOR function, couldn't be learned by this perceptron, because it was proved that the separation of space could only be linear. So it began to be the first winter of neural networks. But a few years later, people saw that when multiplying the number of artificial networks, this limitation could be removed. So that was a new boom for a neural network in the end of the 70s, beginning of the 80s. And a lot of researchers tried to learn. There were good algorithms to learn to teach neural network to compute what we wanted to teach them. But in fact, for images, the problem is that the number of neurons you had to put in order to understand an image was really tremendous. The number of connections between successive layers grow with the square of the number of neurons, so it makes them very difficult to teach. So the solution that arose in the 19th, but took a lot of time to be recognized by the community, were the convolutional neural network. The idea is that help to this convolution operator, the number of weights you have to learn can be very limited, because for a given feature map, you can limit the number of weights to a very small convolution window that can scan the whole image with the same weights. You don't have to have a different weight for every pixel of the input map to every pixel of the output map. It keeps some locality in the image. This is one first point. The other point is that when you have several layers of convolution, the first layer focuses on small details on the image. But since the convolution of a convolution is itself a convolution with a larger receptive area, it's like when we add different layers, it's like if we looked at the image at different levels of resolution. The first layer looks very small details in the images, and the other layers look the images at larger layer, larger and larger, and finally the last layer consider the image as a globality. And the idea of when you give an artificial neural network a given recognition task, the idea is that the weights and the marks that will be used are automatically computed, and instead of being handcrafted and depending on the expertise of the specialists, they will be really adapted to the task you give to the neural network. The first great success of this convolutional neural network is due to a French guy Maria Giulia spoke about, Yann Lequin. His work are dated of 1995. This architecture, Le Net, was published in 1998. So it's a quite long time ago, more than 20 years. But he took at least 15 years to make his work recognized by the community, because it was, well, to work this kind of architecture need a lot of data. And this is often the problem with a neural network. They need millions and millions of data, of annotated data, to work properly, at least at the beginning. So this is a demonstration of Yann Lequin. So the idea is to input the neural network a set of handwritten digits, and what we asked the network was to recognize the digit, and it works better than any other method that was published before. So the revolution of deep neural network can be dated of 2012, because at that time we had this famous ImageNet database. We already spoke about. It's composed of more than 1 million images, 1 million images with about 1,000 classes, different classes. So we have about 1,000 samples of each class, in average. And the other revolution was, this is a GPU, a graphical processing unit, that brings to the computer the power they need to learn, because the teaching of artificial neural network is very long. So in 2012, like every year, the ImageNet large-scale visual recognition competition was first won by a team that used artificial convolutional neural network as for this challenge. They proposed given architecture called AlexNet, and they won the competition with only 16% of error. And the second team was very far away. The second place had 26% of error, almost twice as much errors as the winner. To be considered as a good result, a given class must be in the 5 top of the list of the class among the 1,000 class. It is considered that a given class of picture is considered as well recognized if it's only the first among 1,000, but in the 5 first. So if you look a bit closer to the first layer of this convolution, of this neural network, you see the convolution matrix which replace the handcrafted Sobel operator, for instance, that was used for contours detection. And all these masks are computed automatically and are optimized for this specific task of class identification. On all the different layers, I'll show you another examples for face recognition, for instance, and you clearly see that the first layer are approximately this one. The second layer focuses on eyes and mouth and nose. The third layer focuses on the global face and so on. So you clearly see what I call the the low level at the beginning and the higher level, more semantic when going to more to deeper layers. So this leads to the second part of my talk. I don't know how much time I have.
Comme on a donné un peu plus de temps à Pierluigi, on fait la même chose
or,
avec toi.
Okay. So the first project is and I'll show some pictures and some demos, so it can be very fast. So I'll show you a demo of the main result of the ANR-REV project, which is a project that was led in the last era before deep learning, between 2010 and 2014. It's the aim of this application. It's a smartphone application whose goal was to recognize species of trees from pictures taken from their leaves. So a very short demo. I hope it will work. It's I hope I won't be subject to the demo effect. So this is my smartphone. I launched the Folia application that has to take, that's you. And you are, for instance, someone that walks in the woods and you find a leaf and you take a photo of this leaf. This was taken, bark can also be taken, but now I just take this leaf. You have to help the algorithm to initiate, because there is a large variability in colors. So I have to give an idea of the starting point of the algorithm. So the algorithm tries to compute a compatibility of colors. So it's a kind of semi-interactive process. And here the different steps are details, but of course they can also be skipped. And in a few seconds the shape should be identified. So these are the colors that are compatible with the one I've colored. Then polygonal model tries to approximate the shape. Then a region growing algorithm tries to find the small details of the shape. Well, it's not perfectly segmented, but it's the main contours are approximately found. Then a signature is computed for the left side and for the right side. These two signatures are paired to make it more robust. The base of the leaf is found, the apex also. And there is it was very important for us that we had biologists that told us what is their key for leaf recognition. They have 11 families of shapes. This is a multi-lobé, I don't know the English term, trilobé leaf. There are palmatillobé, lancéolé. This category were mimicked by our algorithm that tried with a very simple polygonal model to find in which category of shapes we were. There are some descriptors linked to the apex and to the basis of the leaf, a symbolic description of the border of the leaf. And that was important for us because we wanted not only a recognition application, but we also wanted to be able to explain why we have done a given diagnosis and why we decide it's this species or rather than this one. There is a kind of pedagogical objective that it's often something that is that artificial neural network don't have. It's a kind of black box that often take the good decision, but when they take a bad decision, they cannot explain why the bad decision was taken. Here, it's much more explicative. So then, you see the current species only in the third position because there was a problem in segmentation, and the algorithm find from the distance between the signatures of shape were closer with this and this one. You see the confidence number are not so high here, and you can see okay, the good one is the third one, and you can have you can see what is well, you can confirm or infirm the determination of the algorithm. Then it can be uploaded to a server. An expert can say yes, the algorithm has taken the good decision, or no, it didn't take the good decision, and that can make the algorithm improve its results because the expert has given the right result. But this can be done in a second time. So that was the folia. Just 5 minutes to show the other project. This new project, which is still ongoing, 2016 to 2020. The project is another collaboration with biologists. It's called Lucy. The title of the project is Lighting Up Fleas to Understand the Complex Transmission Mechanism of Yersinia pestis. Yersinia pestis is the bacteria responsible for the plague, la peste. And the fleas are the insects, la puce, that is the main vector of the plague transmission. The biologists that came to us asked us to help them to analyze thousands and thousands of fleas images. There are three kinds of modalities of images. These are binocular images. These are bright field images of fleas in wells. There are plastic well houses with hundreds of fleas, and they have their shapes have to be analyzed. And these are bioluminescence images where the blood they are fed in is made bioluminescent, and that can be superimposed with bright field images to know where the blood stays, and this is a sign that the bacteria has infected the flea. And we had to combine all these three modalities of the images to follow a given flea during the infection and to answer this question: is the flea a male or a female? is it fed or unfed? Is it blocked or unblocked? When the bacteria has infected the flea, it develops a biological film that makes it unable to digest the blood, and this makes the transmission possible to another rat, for instance, or mouse, which is the other vector of plague transmission. And of course, is it dead or alive? And the biologists told us that human analysis of all the image they planned to produce during the project represented 14 man-years for a specialist. So if a single specialist had to analyze by himself the images, it would take 14 years. So of course, it was our goal to study how to answer to these questions with the help, of course, of their final of the expertise of the specialists. And we tried the two approach, the traditional machine learning approach with handcrafted feature extraction, traditional machine learning operating on this feature to take the final decision, and the deep learning algorithm directly working on flea images. So I'll skip the main tasks of image analysis that allow to segment them. This is a distance transformation, this is a region growing algorithm, this is the labeling of fleas, this is the final segmentation. In this segmentation we have to make the difference between the legs and the body. Once we have the body, we can compute a main orientation, because the flea can be oriented in any position. Then the legs can be segmented. With the body and the legs, we can normalize the orientation, so to make it more easy to compare the shape of the different insects. When this orientation has been done, the difference between males and females is more evident. The male has a small pygidium here that makes a clear difference. So, as expert of image processing, we decided to focus on this particular area. All this has to be done automatically, of course. So we describe the contour of the insect in a polar representation, and we clearly see that there is a difference between quite a smooth contour here and a more prominent contour there. So we derived a feature vector for each insect, which we could input traditional machine learning algorithm like decision trees, random forests, or traditional non-convolutional neural network to make the final decision. The result, we were quite happy with the first result. For gender classification, we were almost perfect, 97.7% of correct classification. It's a bit not as good for the feeding or for the blocking decision, but anyway we were quite happy. But of course we tried to use the new paradigm with which are deep learning. Here you see the deep learning that were used for face recognition, and again you see the different layers that focus on very low level details, higher level, and more semantic result. The problem we had is that we had not enough images, labeled images, to train our algorithms. We had only, for instance, 100 images that were labeled with the final decision, and we had to do learning from these 100 images. the results were quite disappointing, where we tried to make our teaching from these 100 images. The idea when we lack on images is to use the neural network that were trained for ImageNet, for the general visual data classification, and to keep the weight of the first layers unchanged, but to fine-tune only the last layer, the ones that are responsible for the final decision, and to adapt, to transfer the capacity of class identification trained on general shape to our very specific problem of flea identification. And this is quite interesting to see that, for instance, for the blocking, it can be visualized which are the activities that are where the neural network looks at in the picture. And for instance, for the blocking and the feeding decision, it's clear that the algorithm looks inside the flea. For the sex determination, the activation clearly relies on the pygidium. So to take the decision that this flea is a male, the activation function clearly shows that the algorithm looks at these very particular pixels. So the results are, of course, it was our first experiment with a deep neural network, but it confirmed that the results were quite improved, even in the task where the results were almost perfect. It even gained some final precision, and for the other tasks the improvement is even better. So the just final demo I wanted to do is related to our project. I'll try to mimic the situation where I'm visiting a museum, and I'll try again to show you what could be the first brick of augmented reality in the museum. This is the work of an intern master we had in the lab last spring. So this is I am a visitor of a museum, and I'm in front of a picture. And okay, the picture is recognized. This is the legend. What we can't see here is that the image that is represented is not the image I'm capturing, and this can be seen if I put my finger behind. I need my finger disappears under the picture. So this is what is represented here in the video is not the picture that is captured by my camera, but with the picture with the model that is mapped to the acquired picture. And you can very easily imagine that this model could be dynamically replaced by other modalities of acquisition. For instance, the X-rays exploration, or infrared exploration, or illumination with various angles. And this can already be an exploration of the different layers Pierluigi was speaking about, can be explorated by the visitor if, of course, these modalities have been acquired in a first time. The main challenge, of course, and this will be my last slide, what we think is that, of course, we will use convolutional neural network, but we try we will try to not throw away all our expertise in more traditional computer vision descriptors that I think are still very useful. This small demo showed that in our context the augmented reality is not the hard point, because here it's a quite simple identification task. It's not the case, for instance, I worked in a urban context where it's much more difficult. Here we have, we make the hypothesis that we are in front of a plain picture. It would be more difficult in front of a 3D statue, for instance, but with plain objects they can quite easily be recognized, even if the angle of view is not perfect. So augmented reality is not, it's rather a technological brick that has to be integrated in the project. The main difficulties we see will be to select pertinent similarity measures corresponding to the different analysis criteria, color, texture, shape, object distribution, semantic contents, that can, depending on which criterion we want to select, very different picture could augment this picture. We imagine maybe 7 or 10 pictures that could be the most similar image to this picture,